So how many sig figs do each of the following numbers have? 142. Looks like they're all non-zero digits, and there are three of those, Johns. So we have three sig figs. 81.60. This is a final zero after the decimal place. Therefore, this zero is significant. Therefore, there are four sig figs. 7.63 has three sig figs. 0.03, these are just placeholders. Therefore, only one sig fig. Similarly, 0.0086, these are again placeholders, so there are only two sig figs in this case. 3236 has four, that's easy. This one has three sig figs because this zero is significant. Okay. I had some people say, well, there's 1, 2, 3, 4, 5, 6. There's six numbers there, so there's six. No. This is only three. All right. All right. So let's multiply now. Okay. Let's multiply 2.079 times 10 to the second, right, meters by 0.072 times 10 to the negative first. Now, obviously, you won't really write it like this, okay, in real life, scientifically correct way, okay? So, if you were to plug this into your calculators correctly, let's see what we get. So, 2.079 EE second times that by 0.072 EE negative first. And if you work that out, you do get 1.49688 meters. So since you want it in correct sig figs, this one has four sig figs, and this one has two sig figs. So you want to round your answer in two sig figs. So your correct answer should be 1.5 meters. All right. All right. Now we're going to add. We will add these three values. And it looks like they're all in the same units, which is good because you cannot add different units. So that's the first thing you got to check, that if the units are consistent. All right. And then this one, okay, it looks like it has 7,200 seconds, right? This one looks like 83,000 seconds. This one looks like 90,000 seconds. So which one is the least precise digit? It looks like this one is precise up to 100th. This one is precise up to 1,000 place. And this one is precise up to 10,000 place. So since this one is the least precise, we must round our answer to 10,000 place. Okay? Sorry. My paper was moving around as I wrote this. So, when we add all these up, we get, right, 180,200 seconds. So if we get 180,200 seconds, we need to round our answer to 10,000ths place. So here is the 10,000ths place right here. So our answer should be 1.8 times 10 to the 5th seconds as the correct answer. Any questions?
Why are we rounding it to the 10,000th place again?
Because that's the rule. When we're adding and subtracting, we have to round it to the least precise digit. This has precision up to 100th place. So this is more precise, 10 times more precise than this, right? This is precise up to thousandths place. This one is precise up to 10,000ths place. So this is the least precise. This is the least precise digit, which is round 10,000ths place. So we have to round our answer to the 10,000ths place. Okay? If you were to take a look at your note packet and the sig fig rules for adding and subtracting, I think you'll find an example for that. Like for example here, when we are actually adding and subtracting, notice how this one is precise up to, now this is a lot more precise than these values, right? But still, this is going to thousandth of a place. This is also going to the thousandth of a place. This is only going up to hundredth of a place. So this is less precise than these. So we have to round our answer to hundredth of a place. So are we okay with that, David, or?
Yeah, that makes sense now.
Okay. Similarly, subtracting, exactly the same thing. So if you were to write it out, so this is here, here, and here. So this looks like the least precise. All right? We'll come back to 4 and 5. Okay, that's more of an optional, so I'm not going to worry too much on this, but you should really know how to convert all these metric prefixes into standard units, as well as going from standard units to metric prefixes. All right, so determine your height in meters. All right, well, I don't know. How tall are you guys? Since I'm behind the camera and you can't really see me, I'm going to say I'm like 6'3", all right? I wish. All right, 6'3" Mr. Kid, huge. Right? I'm not, but let's just say I am 6'3". You know, that converts to 75 inches. Right? And everyone should have different answers for this. So, since 6 times 12 is 72, 72 plus 3 is 75 inches. So, in 1 meter, right, there are 39.37 inches. I think I gave you this conversion earlier in your notes. Right? So if you multiply these out, the inches will cancel out, giving you 1.905 meters. Okay? So if you really want to, you can actually just say 1.9 meters as a correct sig fix. Okay? All right.
Mr. Ken,
Yeah.
sorry, how do you know that there's two significant figures in here?
Well, yeah, I just use this as like, since like 6'3" and then we convert that into like 75 inches. So I consider this to be my, lowest sig fig, least sig fig.
I see, yeah.
Is that okay?
Mm-hmm.
Yeah.
Got it, yeah.
Most of the times I'll probably let you know. It's like give it to me in two sig figs, and or then you'll know exactly how to give it to me. All right. Let's see. The sun. I think we did this problem already. Well, let's do it anyway. The sun, on average, is 93 million, right? 93 million miles away. If we were to convert this, okay, into meters, we say 1610 meters is equal to 1 mile. So miles will cancel out, okay, giving me 93 times 1610. This gives me 1.4973 times 10 to the 11th meters. Right? Now, using this, now this is using the powers of 10, so I guess this is what the answer should be. Now, you can do this as like 0.15, right? This will be times 10 to the 12th meters, and this is what's 12th? Somebody tell me what 12th is.
It's tetrameter.
Tera?
Tetra.
Yeah, tera, right?
Yeah.
Terameters. Or you could say simply 1 point, well, you could say 150, oops, 0.15 terameters, or 150 gigameters would also be the same things. All right. All righty. All right, moving right along. Let's take a look at number 8. Now here, when you're working on this, the units, they're all over the place. So you have to really convert these into the standard metric unit. In this case, happens to be meters. Therefore, we'll leave this one alone. So we got 1.00 meters. However, if we want to change centimeters into meters, so we have 142.5 centimeters, and if we convert that into meters, in 1 meter there are 100 centimeters. Therefore, it is 1.425 meters. So here I have 1.425 meters. What about this one? This is a micrometer, so this is 10 to the negative sixth, right? So if we were to look at this, like 1.24 times 10 to the fifth micrometers, if we want to convert that into meters, in 1 meter, there are 1 million micrometers in 1 meter. Okay? Therefore, notice how the micrometers will cancel out, and this will give me 0.124 meters. Okay? So here, 0.124 meters. So I'm going to add these. And when I add these, I get 2.549 meters. But which digit or which placement is the least precise? All right, good. This right here is the least precise, so we should really round our answer to the least precise, because this goes up to hundredth, this one goes to thousandth, this one goes to thousandth, so the hundredth is the least precise, so we should round our answer to 100th. Therefore, our answer should be 2.55 meters as our answer. So is everybody okay with that?
Shouldn't we use the precision from the original numbers given?
Yes, I did. It is.
Wouldn't it be just the 10th place then?
No, we're not multiplying this. It's not 10th place this is actually in the micrometers, right? So we have to use the correct units and place them in the correct unit form. So if you were to use this value right here, or this value right here, right? So this is in centimeters. So this is decimeter, centimeter, and this is like millimeter. And this here is, this is decimeters, centimeters, millimeters. Okay? Because even though it is given to you as a scientific notation, they are only precise up to whatever the value that's given to us. Does that make sense, Aiden? Yeah? That's why I spreaded them out like this, just so you could see it. Yeah, it is tricky. Adding and subtracting, I think, is more tricky than like just multiplying and dividing. Okay, any other questions? Liam? It sounds like you're talking, but I can't hear anything.
My bad.
You're bad. No questions? Okay. All right. What about number 9? What about number 9? All right. Let's take a look at number 9. Well, how many seconds are there in 1 year? Well, let's work with what we know. In 1 Earth year, so 1.00 year, okay, I know there are 365 days, but I know somebody's going to say, well, Mr. Kim, technically there's a leap year, so you have to have like a quarter day added to each year to add up to a leap year in every 4 years. Fine, if you want to be that precise, you could do that, right? There are 365.25 days, if you want, right, per 1 year, right, on average. Well, I know for sure there are 24 hours in 1 day, average. And I'm going to say there are 3,600 seconds in 1 hour. Every year I catch somebody saying there are only 60 seconds in an hour. Please, don't be that person. So if you do that, notice how the hours will cancel out, days will cancel out, years will cancel out, and gives me big number. 3155760 seconds. And if you want to do this in correct sig figs, since this is what's given to us, these are all conversion factors, so we're not going to worry about these sig figs. We have to work with what we have. So let's round it to 3 sig figs. So we got 3.16 times 10 to the 7th seconds as our correctly rounded sig figs. And then for part B, it asks, okay, how many nanoseconds are there?
Mr. Game, sorry, I had a question.
Yeah, question.
So why wouldn't it be one significant figure? Why is it 3?
Because this has 3,
Oh, that's correct. Yes, sorry.
right? 1.00. So these zeros are significant.
Got it, yeah.
Good? All right. So since we already know how many seconds we have, right? We're going to convert that just into nanoseconds. So like 3.16 times 10 to the 7th seconds. This is something that we already know that we got answer for, right? We want to get rid of the seconds. In 1 second, there are 1 billion nanoseconds in 1 second. Right? There are 1 billion nanoseconds in 1 second. So when we multiply this out, we will get 3.16 times 10 to the 16th nanoseconds. Okay. And then for part C, how many years are there in 1 second? Wow. How many years are there in 1 second? Well, in 1 second, we know there are 3.16 times 10 to the 7 seconds in 1 year. Therefore, if we multiply it out, the seconds will cancel out. And it'll give me 3.17 times 10 to the negative 8th years in 1 second. All right. Next, what are the area and the approximate uncertainty of a circle of radius 2.8 times 10 to the 4th centimeters? So since this measurement here is given to us without the percent plus or minus uncertainty, this is the uncertain value. So if we were to write this radius with the uncertainty, right, we have 0.1 plus or minus 0.1 times 10 to the fourth centimeters as the uncertain value. So this can be written as 2.8, right, plus or minus 0.1 times 10 to the fourth centimeters. That means if I were to overestimate, I'm going to say R is equal to 2.8 times 10 to the fourth centimeters. But R plus, which is the overestimation, is 2.9 times 10 to the fourth centimeters. And underestimate, R minus, we can say that's 2.7 times 10 to the fourth centimeters. I'm going to use just the overestimation one just to be, just to simplify it. Okay? You can use either one, but I'm going to use the overestimated one. So let's first calculate what R is. What the area is with just using just R, with just this. All right? We know R is 2.8 times 10 to the fourth centimeters. So the area of the circle is equal to pi r squared, not 2 pi r, sorry. And I'm going to distinguish the difference of this area of a circle without the uncertainty. Okay? So the area without the uncertainty is pi times r squared, which is 2.8 times 10 to the fourth centimeters squared. And we get our answer to be, okay, we get something like 2.463 times 10 to the ninth centimeters squared. Now we're going to actually use this radius to find the area for that. So if we were to do this, I'm going to represent that R as R plus. So R plus is 2.9 times 10 to the fourth centimeters. So the area of the R plus is equal to pi R plus squared. Okay? So here, pi times 2.9 times 10 to the fourth centimeters squared. And then if you do that calculation correctly, I believe you get something like 2.6, right? 2.6 for 2 times 10 to the ninth centimeters squared. So now that we have, so think of this as the theoretical value, okay? And think of this as the measure value, okay? So we can now calculate, okay, the percent uncertainty. So here, okay, we have A plus minus a theoretical, divide that by a theoretical, right, times 100%. Okay? So this is percent uncertainty. So here, I mean, I guess you can actually just, if you want to, you can write the area and the approximate uncertainty. This is going one step further than it should, actually. I'm sorry. So you could say the area is equal to, you could say simply A naught, right, plus or minus whatever the difference this is. Okay? The difference of this two is like, 0.18. Okay? So you could say A plus minus A naught. You could say it that way. So that can be said as 2.46, right? Plus or minus, right? 0.18 times 10 to the 9th centimeters squared. So this is what they actually are asking for, this number right here. Okay. So this value here came from this minus that as the uncertain value for the area. This came straight from this. Okay. So if you want to truly round this to the correct sig figs, it should be 2.5 plus or minus 0.2 times 10 to the 9th centimeters squared. All right. Since I gave you this, see if you can figure this out as a practice, okay, on your own. And I'll give you the answer so you could actually check if you did it correctly. It's about 7.3% error. Okay, so this is the answer. Okay? Now that I showed you how to do that, why don't you guys do 11, and then I'll give you homework, or maybe even like a mock quiz or mock test, so you can see what it's going to look like. Let me see. It should be on Schoology, if I can find it. Let me see. All right. Can you guys see the Schoology page that I put up?
Yeah, I can see it.
Good. So if you go to, take a look at this. This is a good practice for you guys to do if you want. Okay? And that is located in Chapter 1 Honors, Chapter 1 Homework. Okay? Give it a shot. We'll go over that if you want before the test. All right? On Friday. So give this a shot. All right. So I'll take that out. All right. I'll help you set this up. Okay. So since now they give us this R radius with the uncertainty value, we will use this uncertainty value. Now, if they didn't give us this here, we would have probably said plus or minus, there shouldn't be two zeros here, plus or minus 0.01. But since they gave us this 0.08 as the tolerance, so we can use that. So our R with plus the uncertainty is equal to, right, 3.94 meters. And we will compare this with R without it, which is just 3.86 meters, right? So we will compare these two for the percent error. Okay? So here, if I were to look at a sphere with radius R, right? The volume of, so this is without the uncertainty, volume is 4/3 pi R naught cubed. Okay? So we will use this value into here. So V naught, volume naught, is equal to, right, 4/3 pi times 3.86 cubed. So volume without the uncertainty comes out to 240.918 meters cubed. Now, if we were to find volume with the plus radius, it's going to be 4/3 pi times 3.94 cubed. So the volume with the plus radius comes out to 256.199 meters cubed. So the percent uncertainty, right, is equal to, I should have used a different color, sorry. So percent uncertainty is equal to, right, it is V naught, right, minus V plus over V naught, right? So times 100%, right? So that is equal to, right, 240.908 minus, right, 256.199, right, divide that by, right, 240.908 times 100%. So that comes out to, I believe, 6.35% as the percent error. Yes, Sarah?
Is the uncertainty equation so it's different than the percent error?
They're same thing, exact same thing actually.
Then wouldn't the V's be switched at the top?
Yeah, it shouldn't matter because
Oh, because it's
it's
absolute.
absolute value. So yeah, so it shouldn't
Okay.
matter which one you subtract from what. Yeah, good question. All right, so we are finished with chapter one. Yay! All right. So Friday, I would like to go over like any last minute details with you, closing out chapter one, and then we will have an assessment towards the end of the period, and um, yeah, that's it. Any questions?
What is that assessment gonna look like?
There will be two parts. One's going to be like multiple choice part, and then there's going to be a free response part. The free response part, you're going to have to print it out at certain time because I'm going to give you a window of certain time. And then once you print that out at certain time that when it's posted, then you have to upload it within that time window to get proper credit. All right? If you have IEP or 504, then you have more than enough time because that free response should not take you more than 20 minutes. But I will give everyone hour and a half. Okay? All right. Any questions? Ishan, you have a question?
Yes. So over here, shouldn't be 240.908 minus 256.199 over 256.199?
No, because this
So,
is this is the theoretical value without the uncertainty.
oh, okay. So which one is the measured value in here?
This will be the measured value. This is the
Okay.
theoretical.
Wait. So that's like plus 0.08, 3.86. So
Yeah,
I
it
have to go
doesn't.
like
Yeah, I
add.
switched this. I switched this, but it
Okay.
shouldn't matter because it's under the absolute value sign.
I agree, but how do you know that 3.86 plus 0.08 is the measured value?
I'm just going to pick one
Why wouldn't it be?
to be one with the
Okay.
uncertainty.
All
Okay.
right. Uh-huh.
And then that will be like more of a measured value because that's, and then I'm going to consider that to be theoretical. Because let's say you're
Okay.
measuring something, you measure this, right? And then, but your tolerance level is really like your instrument is only got this much of tolerance. Then you could switch it around, but it's still the answer would not come out that much different. Okay.
Thank you.
All right, Yanni.
What is the format of the quiz or the test?
There'll be some multiple choice on Schoology, and then free response that you have to print out on given time. And then as soon as I upload it, you'll have hour and a half to print out, solve it, and upload.
All right, thank you.
Yep. Any other questions? All right. We're like running overtime here. Like we're 2 minutes overtime. Great. Thanks for joining me. Um, I guess I'll see you guys Friday. All right. So hopefully work on some of these questions. See if you can work it out. All right. If there are any other questions, you can remain behind. I'll stay behind for another minute or two. If not, have a wonderful day, everybody.